Paralysis of all four limbs from injury or disease can severely limit function and independence. Even when a person has become paralyzed due, for example, to spinal cord injury, neural activity in his or her motor cortex changes as they imagine moving their paralyzed arm or hand. Intracortical brain-computer interfaces, or IBCIs, can use signals recorded from electrode arrays placed in the motor cortex to decode the direction of imagined movement. IBCIs have enabled individuals with tetraplegia to control a computer cursor and to engage in tasks such as on-screen typing. IBCIs have also been used to control a robotic arm, and when driving muscle stimulators, even a person's own arm and hand. Current state-of-the-art decoders deployed in human IBCIs assume that the neural data is distributed according to a Gaussian, whose mean is a linear function of the intended vector of movement. This linear model is justified by pioneering studies of the motor cortex of non-human primates by Georgopoulos. These studies show that each neuron's activity is highest for some preferred direction of movement and lowest in the opposite direction, with intermediate activity well modeled by a cosine function. While the cosine tuning model is approximately correct for many individual neurons, many other neurons do not display such cosine tuning, and neural features used for IBCI decoding may capture the pooled activity of several neurons. We introduce a new likelihood that captures the feature's potentially multimodal dependence on the intended angle of movement. In addition to providing better fits for channels with complex or multimodal activity, the flexible tuning model also provides good fits to apparently cosine-tuned signals. The observation underlying our multiscale dynamical model is that the update rate used for neural decoding is much faster than the rate that the participant's on-screen goal position changes. In addition, frequent but small adjustments of cursor aim angle are required to maintain a steady heading. State-of-the-art Kalman filter approaches to IBCIs cannot capture these multiscale dynamics, since they assume first-order Markov dependence across time and do not represent goal position. The MSSM decoder, by contrast, represents goal position in addition to the intended angle of cursor movement. Through the use of Semi-Markov dynamics, the MSSM enables goal position to evolve at a different rate than angle, while allowing for a high rate of neural data acquisition. In this way, the MSSM can integrate across different timescales to more robustly infer the goal position and the intended angle. We evaluate mean squared error as well as two metrics that describe the smoothness of cursor trajectories, orthogonal direction changes and movement direction changes. As seen in the videos, the MSSM decoder yields an appreciably straighter and smoother trajectory than the Kalman approach. We hope that this MSSM decoder will become the basis for a novel and even more intuitive method of controlling external or internal devices with intracortical BCIs.